This graph plots a major collision course in modern AI. On one track, you have parameter counts, the raw size of the models, climbing steadily. On the other track, you have the computational budget, or flops, required to train them. To make a model smarter, we make it larger, but the financial and electrical costs are rising at a rate that is becoming unsustainable. The culprit is an architecture known as the dense transformer. In a standard language model, every single parameter fires to process every single incoming word. If you feed the network a simple sentence, the entire massive brain lights up to read it. Imagine a corporation with 10,000 employees. Every time a single customer service email arrives, every single employee has to stop what they're doing, read the entire email, and weigh in on the response. That is the inherent inefficiency of a dense network. Because of this architecture, we are rapidly running out of physical supercomputers capable of the brute force computation required for the next generation of AI. There is a hard physical limit to how many chips we can chain together before the power grid simply cannot support the load. To keep AI progressing, researchers had to find a way to decouple a model's size from the computational power required to run it. They needed a way to increase the parameters without increasing the energy consumed. The solution relies on sparsity, specifically an approach called mixture of experts. Instead of everyone in the office reading that customer service email, a receptionist intercepts it at the door and routes it directly to the one specialized department best equipped to handle it. Early models used top 2 routing, splitting data to 2 experts simultaneously, creating massive overhead. The switch transformer uses top 1 routing, sending each token to a single expert. This slashes computation, allowing engineers to add hundreds of experts without increasing total flops per token. By routing selectively, the switch architecture demonstrates that we can multiply an AI's specialized knowledge without expanding the computing budget. But building a sparse model introduces new engineering hurdles. The first is load balancing. If the router favors certain experts, it creates a bottleneck, flooding the grammar expert with thousands of words, while the math expert sits idle. When a node gets overloaded, it simply drops the data. To fix this, the team introduced an auxiliary loss penalty and a mathematical buffer called a capacity factor. If the router plays favorites, the penalty hurts the model's overall score, forcing it to distribute the workload evenly across the network. The second hurdle is training instability. To keep models fast, engineers usually train them using a low-precision math format called bfloat16. However, sparse models are fragile. Pushing hard routing decisions through low-precision math causes the model to diverge and crash. The researchers bypassed this with selective precision. They isolated just the tiny routing mechanism and forced it to run in highly stable float32 precision. Once the token is routed, the rest of the massive network continues in fast, efficient bfloat16. Bypassing these low-level instability and balancing hurdles provided a stable framework for training sparse models at scales that were previously unreachable. To measure the performance gains, the researchers compared the switch transformer against Google's highly tuned dense baseline model, the T5. They gave both models the exact same computational budget and tracked their progress. The results were stark. The switch architecture achieved the same language quality as the dense T5 model, but it reached that threshold 7 times faster. This efficiency extends to multilingual data as well. In tests spanning 101 different languages, the switch model maintained a 4-time speedup across 91% of the languages tested. This diagram illustrates how the researchers combined 3 different types of parallelism across TPUs. By physically dividing both the data batches and the unique model weights across a mesh of hardware cores, they reached a scale of 1.6 trillion parameters. However, a 1.6 trillion parameter model is too large for consumer devices. To address this, researchers used distillation. They successfully shrunk the giant sparse model by 99% into a small, dense model, while still retaining nearly 30% of the sparse model's performance gains. The final switch transformer results clearly indicate that increasing parameter counts no longer requires a proportional increase in computing power. Sparsely activated routing allows for massive increases in model size without the typical computational penalties.